I'm going to start by saying what is the key idea in the algorithm. It's kind of, in binary search, you're like, I don't know, testing different locations in powers of 2, but there's a kind of a check to see what's going on with your parameter. And what I'm about to tell you now is like the checking step. And it won't be exactly clear at first why we're looking at this key idea, but hopefully it'll become clear soon. So the key idea, which take my word for it is relevant, is the following. If theta happens to be a quote unquote medium angle, okay, and a medium angle, I'm inventing this terminology just for this lecture. So by medium, I mean between 30 degrees and 60 degrees. 30 degrees and 60 degrees. Then it's very easy to notice this. Okay, so first of all, you might say, like, this is a weird thing to say because, like, we're already assuming from the get-go that theta is less than 30 degrees. So it seems completely irrelevant. Just bear with me. It's gonna be relevant soon. Or for now, perhaps you don't assume this for like 1 second. Okay, so the idea is, how can you maybe detect that this mystery rotator is rotating by between 30 and 60 degrees? Actually, any ideas? I guess I'll erase this. In Germany, they have like this system where they use blackboards. Oh yeah, sorry, just 1 second. I'll tell this dumb anecdote. And like they write on them, and then like every classroom comes with like a bucket of water and a squeegee, and like every time they clean the board, they like squeegee it and then like dry it, and it looks very elaborate and formal, but it does make the chalk really easy to see. Anyway, what were you gonna say? Yeah, exactly right. I think you got it exactly right. Basically, I mean, I'll write it out, but if theta is really close to 0, the idea was like, yeah, like, make ket 0, like make a new qubit and do this mystery rotation. So now the angle is theta, and then do extract and see if you get outcome 0 or 1. I mean, if theta is really close to 0, then you'll probably, do this 10 times. You'll probably see the outcome 0 every time. If theta is like really close to 90 degrees, you'll probably see the outcome 1 every time. But if it's like medium, you'll see like a healthy mix of 0s and 1s. So you can be like, oh, I'm getting a healthy mix of 0s and 1s. Theta is like somewhere in the middle between 0 and 90 degrees. Indeed. So let's exactly work that out. So I'll make this routine, which I'll call is medium. And this is medium. I'm going to pass into it a function. It's very sophisticated move. Sort of this is medium subroutine takes in like a rotation function. In this case, mystery rot. And yeah, I'm just going to do this kind of statistical algorithm where like, okay, I'll like start count. That's just like a normal variable, classical variable 0. And I have like 100 in my notes. So let's do 100 trials. We'll make a new qubit A. And we'll apply the mystery rotation to it. Okay, so now A's state vector is at angle theta. And then we'll do extract all. And then let's count the number of times we see the outcome 1. So if the outcome of this extract all is 1, then let's increment count. Okay. This is a classical line of code. This is classical. This is classical. These are quantum. That's fine. And then at the end, we're going to basically check to see if we got like a medium number of 1s on the scale of 0 to 100. So if, let's say the count is between 20 and 80. Then we'll return yes. else we'll return no. So we're trying to detect if theta is like a middling angle. Okay, let me also, by the way, say that like for all these algorithms, like we have these like side remarks like with high probability, and we're going to talk later about like how this algorithm works with high probability. We're going to dig into this in a second, but like whenever you have like a statistically kind of algorithm, it's sort of inevitable you have to allow some chance that your algorithm fails completely. You know, if you're flipping a coin and trying to tell if it's like a fair coin, even if it is a fair coin, there's some half to the power of 100 chance that like all 100 heads come out heads, and you're like, oh, this isn't a fair coin. It's very unlikely, but you know, you have to allow for these small probability events. Okay, so let's work out some properties of this algorithm. Oh boy, what a world. Okay. All right, so fact one. So if theta really is medium, then I claim the is medium algorithm returns yes with high probability. And here, maybe specifically, we want to be careful. I'll say probability at least 90%. So, all right, why is this true? Well, in one measurement, this is like a measurement here. In one of these, the probability of getting an outcome of 1 is, well, we already know what it is. I mean, this makes the state vector at angle theta from ket 0. I mean, the picture is like 0. This is your state. This is theta. This is 1. Okay, and this height here is sine theta. So that's like the y coordinate. And so the probability of getting ket 1 is the square of this, which is sine theta squared. Sine theta squared. Okay, and so we're assuming theta is medium. So it's between 30 degrees and 60 degrees. Wow, it's a real palimpsest here. This probability is between sine of 30 degrees squared and sine of 60 degrees squared, which, if you remember your trigonometry, is between 1/4 and 3/4. Okay, so we expect, I mean, so this thing, this outcome equals 1, like somewhere between 1/4 and 3/4 of the time. So if you're doing this 100 times, you expect to get count between 25 and 75. And we're checking to see like a more liberal thing that's between 20 and 80. So it should work. I'll just write that. So we expect count between 25 and 75. And if you crunch the numbers, which I did on my computer, and I'll spare you it, you can check that the probability it's less than 20 or more than 80 is less than 10%. So with high probability, you just take my word for it, indeed greater than 90%, count is between 80 and 20. Okay, does that seem all right? Good. So now let's work on the other side of this. So Normally, at first, you'd like to say, like, okay, this algorithm is supposed to be detecting mediumness. We show that if theta is medium, there's a high chance it returns yes. You might expect me to now say, oh, if theta is not medium, there's a high chance it returns no. But that's not quite what I'm going to say. And maybe you can think about why that's not quite what I'm going to say. Let me write what I am going to say. Fact 2. If theta is not medium-ish, then this algorithm is medium, returns no with high probability. Again, let's say bigger than 90%, where medium-ish is like another new term I invented. And it means between 22.5 degrees and 67.5 degrees. Okay, so I mean, so I can split it into thirds. This was like medium. But then like maybe this slightly wider range is like medium-ish. Like this whole range. Okay, so, well, let me briefly ask you now, like, why didn't I just put medium here? Yeah. Yeah. The point is, in these statistical estimation things, like imagine theta was like, maybe it was 30.00000001 degrees, or maybe it was like 29.999999 degrees. So if you're really trying to check if is it literally medium, did I delete the definition of medium? I guess I did. But anyway, if it's like literally medium or literally not medium, then like you have to know the difference between is it 30.00000001 or is it 29.99999. And these are like, you know, almost imperceptibly different. So no algorithm is going to, unless it makes like zillions and zillions of calls, is going to be able to tell the difference between these like unbelievably close angles. So it's not a good idea to like try to like have this extremely bright line cutoff between medium and not medium. So that's why we have sort of two different cutoffs. There's like a gray area between like these bounds and these bounds. Okay, but we'll see that that doesn't like really upset us, or it doesn't like make our the algorithms not work or anything. It's just it's like a little bit annoying to keep track of the difference between medium and medium-ish, but we got to do it. Okay, so let's prove why this fact is also true. Okay, so why? So not being medium-ish means means that either theta is smaller than 22.5 degrees or theta is greater than 67.5 degrees. And I shouldn't mention this before. I don't think I wrote it down, but for this whole detecting medium thing, I am assuming this theta is between 90 degrees and 0. Okay, so it's either, if it's not medium-ish, then it's either between 0 and 22.5, so it's like in here, or it's between 67.5 and 90 degrees, so it's like in here. But intuitively, you know, if it's in here, that means when you do these measurements, like most of the time you'll get 0, and so you'll probably have count bigger than 80. And if it's in here, then when you do these measurements, most of the time you get 1. So like probably you'll count will be smaller than 20. So again, you have to like crunch the numbers, but I did that for you. So then each measurement has a probability of the outcome being 1, either less than whatever sine of this squared is, which is apparently 0.147, so 14.7%, or greater than whatever sine of this thing squared is, which apparently is 0.853 or 85%. So we expect that count is probably either less than 15 or greater than 85, typically. And again, if you crunch the numbers a little bit, you can show that, if one of these two things is the case, then the chance that you'll actually, funnily enough, see that count is between 20 and 80 is less than 10%. Less than 10% chance it's in 20 to 80. Okay, so a little bit of number crunching and you get this. Okay, so let me write it over here. So the upshot of these two facts is we can reliably, I'm going to put this word reliably in quotes because I'll come back to it, distinguish the case, theta is medium, and the case theta is not even medium-ish. Okay, so if theta is medium, you run this algorithm, it'll very high probability say yes. And if theta is not even medium-ish, you run this algorithm with high probability, it'll say no. Hey, if theta is in this gray area between medium and medium-ish, I don't know, the chance it says yes or no will be somewhere between 10 and 90%, but we'll leave it at that. Okay, any questions? Good. Okay. Now I have to do one of these slightly fudging things that I said last time I might get into, which is this word reliably. I mean, I put it in quotes, but if you look at the, when you crunch the numbers, it literally meant probability greater than 90%. Now, I would like to make a temporary assumption for simplicity that this reliably means 100% reliably, which it doesn't. This fact that you can distinguish these two cases, this algorithm fails 10% of the time at doing the right thing, but let's temporarily pretend it fails 0% of the time. And I will explain later why this temporary pretend is not really a big deal and we can fix it. But for now, let's just pretend it. So temporary pretend. I mean, basically, the reason it's okay to pretend it, we'll get to it later, is you can always make this 100 like a million if you want. And that'll make the probability, more and more reliable. But anyway, let's pretend that reliable here equals 100% reliable. Okay, and so therefore, if is medium, you run it on mystery rot, says no, or returns no, then theta is for sure not medium. And if it returns yes, then theta is for sure at least medium-ish. Okay, so this is the same as this if reliable meant 100%. Okay, so we're just going to kind of like put this in our pocket and use it as a subroutine going forward.